This is the first video for section 4.3, probability. In this video, we will identify possible outcomes of an experiment, determine the number of outcomes in a sample space, determine an equally likely sample space, and do the first example of computing theoretical probabilities. So before we begin these examples, some definitions are necessary. So the first definition is simply, what is an experiment? An experiment is any action taken to collect data. So for example, your experiment could be to flip a coin. Now there are many examples of experiments, right? This is just one. So an outcome is a result from the experiment. To continue with our flipping a coin example, an outcome could be heads, right? That is one of the results that could happen when you complete that experiment. The set of all possible outcomes is called the sample space. To continue with the flip a coin, your sample space would be heads or tails, right? Those are the two possible things that can happen when you flip a coin. A sample space in which each outcome has the same chance of occurring, that is called an equally likely sample space. Here I will have to give you two examples. So an equally likely sample space is flipping your coin, a standard unweighted coin, because it's equally likely that that will land on heads or land on tails. An example of a not equally likely sample space is winning the lottery, right? Two things can happen when you buy a lottery ticket. You could win or you could lose, but those are not equally likely, right? It is more likely that you will lose the lottery, less likely that you will win. So all of that is written here. Let's put that right there. That equally likely is that example of getting heads or tails when you flip a coin. Not equally likely is winning the lottery or not winning the lottery. An event, that is a subset of outcomes from the sample space of an experiment. And you will see what we mean by event when we get into the examples here. So example one is to simply work with some of these definitions. So given the following scenario, state the experiment, an equally likely sample space, and the outcome. So what if you roll a single die and the result is 1? So the experiment is rolling a die, right? That is the action you are taking. The sample space, the set of all possible things that could happen, is 1, 2, 3, 4, 5, 6, right? With a standard 6-sided die, those are the numbers you could roll. And then the specific outcome we're interested in is rolling a 1. So all of that is summarized here, right? Again, your experiment is rolling a die. The sample space is the numbers 1 through 6, and the outcome is rolling a 1. So what if your experiment is flipping a single coin and the result is heads? So now here your experiment is flipping a coin, the sample space is heads or tails, and the outcome that you're interested in is flipping heads. Okay, moving on. So example 2, this falls under the outcomes and visual representations section of 4.3. So in this section, we're thinking a little bit more about how can we visualize what's going on here, right? To kind of think about more complex experiments, how can we get a visual to help us determine the number of outcomes possible? So for 2A, a card is chosen from a standard 52 card deck. The card is replaced and a second card is chosen. So here I'll just think about that like I choose my first card and you have 52 choices for that first card, right? There's one of 52 cards you could choose with that first one. And same thing with that second card. There are 52 choices you could make or 52 cards you could draw with that second card. So the number of outcomes is simply 52 times 52, or 2,704 outcomes. Example 2b. Maddie draws a marble from a bag containing 3 blue, 2 red, and 1 green. Maddie sets aside that marble and draws a second marble. How many outcomes are possible? So a table is one way to visualize this. So in this table, I have listed the 3 blue, 1, 2, 3 blue, the 2 red, and the 1 green. I have that listed in this first vertical column here. And then in the first horizontal column, the header of this table here, we have again the 3 blue, the 2 red, and the 1 green. Now it is important that Maddie sets aside that first marble and then draws the second marble. This means that it is not possible to draw the same blue marble twice or the same red marble twice, right? That means that these boxes here along the diagonal can't happen, right? Because that would be drawing like the first blue marble and the first blue marble twice. You can't do that. Or drawing the second blue marble and the second blue marble, right? You can't do that. Since Maddie sets aside that marble and draws another. So I have to not count all of these boxes along the diagonal, simply because those boxes would be drawing the same marble twice. And the way Maddie is doing his experiment, he's not doing that. He's taking one marble, setting it aside, and then drawing his second. So now we can simply count the number of boxes left, right? And I think we get 30. So 30 outcomes. The other way I could see that is I could say, okay, on the first draw, Maddie has 6 marbles he could choose from. And then on the second draw, there's only 5 marbles that Maddie can pick from. And that's because he keeps that first marble. So 30 outcomes possible. All right, before we continue with our final objective, find the probability, some definitions are required. So probability is the value that reflects the likelihood that an event will take place. So the probability of event E is simply the ratio of the number of outcomes in event E by the total number of outcomes in the sample space. Probability is a value between 0 and 1 inclusive, meaning probability could be 0 or the probability of an event could be 1. The first type of probability we will compute is theoretical probability. So theoretical probability is using theory to complete your probability. So these are not results from actually doing an experiment, but this is in theory, what do we expect to happen? Okay. Example 3. Find the following theoretical probabilities when rolling a single die. So first, the probability of rolling an even number. So that is how we write this. We write the probability of rolling an even number that's the event E that you're interested in. So this means to find this probability, in the numerator, you want to count the number of ways this can happen, the number of ways you can roll an even number. So there are 3 outcomes with even numbers, right? And then in the denominator, you want to count the total number of outcomes of the sample space. So there are 6 outcomes in the sample space. So that means that to find this probability, you are taking 3 divided by 6, or 1/2. So you have a 1/2 probability of rolling an even number. Again, to find that theoretical probability, you're counting the number of outcomes in the event that you're interested in, divided by the total number of outcomes in the sample space. We will finish example 3 by finding the probability of rolling a negative number. So again, the event I'm interested in is rolling a negative number. There are 0 ways to do that, right? On your standard 6-sided die, your numbers are 1 through 6. None of those are negative. So there are 0 outcomes with negative numbers. Again, divided by the 6 outcomes in the sample space. So 0 divided by 6, or you have a 0 probability of rolling a negative number. So events with a 0 probability are events that will never happen, right? It will never happen when you roll a standard 6-sided die that you roll a negative number. This concludes example 3, and this concludes video 1.